All right, let's get started now. So I'm going to talk about, in this Lab 2 description, I have these learning objectives listed. I'm just going to try to go through this list here and talk about each one. And this corresponds with the book. If you happen to be reading through the book, this is chapter, 3 or 2? I don't remember which one it is. All right, the notion of a data type. So we've looked at things like we've declared integers, integer I equals 3, and then we have a double x equals 4.5. So this is data. So this is a variable I. It's like a label which is associated with computer memory. That has in it a representation of some value, and currently the value is 3. And then here's another separate label, x, that's also associated with some memory in the computer, and which is in a state that represents some value, in this case 4.5. But these are different. You know, I is called an integer, and x is a floating point number. So they have different representations, you know, in the hardware. We could also have strings. So we can have a string, say s equals hi. And now the string is a data type, and s is an instance of that data type. We can print s. ENDL, that's end line. That's a new line. Let's print a new line. We could also print the other values as well. So we can print x, or I, and x, and s. 3, 4.5, and high. So these are called data types. There's another data type which you'll need to know in this class, and that's bool. And Boolean takes on 2 values. It's either true or false. It only has 2 states. And the integer I has many states. How many states does it have? Well, an integer is represented by 4 bytes. So it would be, let's see, 1 byte has 8 bits. So 4 of those makes 32 bits. So there's 2 to the 32 different states that I can be in, the memory that I is associated with that memory. There's 2 to the 32 different states that memory can be in. The bool has only 2 states, true or false. Actually, in most languages, bool is strictly true or false, but in the C++, bool and int are similar. But I don't want to get into that detail, actually. And a string, there's really no limit to a string. So a string, when you create a string, you're allocating memory in this area called the heap, or dynamic memory. And a string can be any size. I mean, limited to, you know, what's allocated to your process, perhaps. And a double precision floating point value, and we just say double for short, that's represented by 8 bytes. So it's double the size of this int. There's also a float, too. This is a single precision floating point value called float. This is double. So this is half the size. Y is half the size of x. Y has got 4 bytes, just like an int. And it's the same with integers. You can have We can have a long int, that's 8 bytes. And you can have a short int, that's 2 bytes. And you can have a char, or character, and that's a single byte. You can't allocate something smaller than a byte, and a byte has 8 bits. So there's 2 to the 56, 2 to the 8 rather, 2 to the 8 possible values that C can represent. In the old days, 8 bytes was enough to represent all of the symbols that were needed, like in the English language. And but since the old days, computers have become widespread, used all over the world, and need to represent many different languages. So the strings in programs need to represent many different languages, and some languages have a large number of characters. For instance, Chinese has many characters in it, 10,000, something like that. So a single byte isn't big enough, so we need to use different ways to represent characters from those languages. So we use other things, and I'm not going to get into that. So you have different kinds of characters and different kinds of strings. I'm not going to get into that, because it actually gets really messy. So these are the data types that we're going to be concerned with. Maybe we won't use a long, we won't use a short, maybe we'll use a long. By the way, an abbreviation is just long I, that's typical. We might use a long at some point later at the end of the course. And we will not use a float in this class. We don't have any reason to use a float. And, but we'll use bool, string, double, char, long, and int, maybe long. So these are data types. And there are two different, there's a division of data types into two basic types. There's the primitive and the complex data types. Oh, this won't work here. This has to be something like a J. So the integer, in long integer, char, double, those are primitive data types. Bool is a primitive data type. They are represented in memory in a simple way. They can reside completely on what's called the stack when a program runs. And and the operations that are defined for the primitive data types are the common symbols that we're used to, like plus and minus, times, divided by, modulo, and so on. And but now string is not a primitive data type. A string is a complex data type. So when we have a string value, there are behaviors or functions associated with instances of the string data type. For example, we can print as, but we can also print the size of as. We do it like this. Whoops, I got that wrong. So we use this dot notation. S is a complex data type. That means there's functions that we can invoke relative to instances of that data type. We use this dot notation. So you have the symbol for the data type instance, S in this case, dot, the name of the function, and then an argument list. And this is a function. And there's nothing in this argument here, but we could have. Normally, these functions take some arguments to them, but it could have 0 arguments. In this case, the size function has 0 arguments. Let's take a look at that. See, the size of S is 3. All right, it's there's one character here, H, I, and period. So there's 3 characters in that string. The size of S is 3. Let's look at some, there's another function, that's substring. Let's see if I can remember it. Substring. And there's a index of the first character in the string, and then the number of characters in the substring. So let me change that to 2. So this character H is in position 0, I is in position 1, and period is in position 3. 2. So there's 3 characters, 0, 1, and 2. Start counting at 0, so it gets confusing. Normally we start counting at 0. A computer starts counting at 0. Humans, they start counting from 1. But computers, they start counting from 0. So when we code, most programmers try to count like a computer. It's easier to write your code, especially low-level code. If you count like a computer, which is to start from 0. And then in anything that's a sequence, like a vector or an array or a string, there are positions in that sequence, and the positions are given integer labels, and they all start at 0. So this is position 0, 1, and 2. So starting at position 0, take 2 characters. So that should print HI. See, this is the substring. So it's a substring function. Once again, S, which is a string, is a complex data type. So it comes with these functions that we can invoke relative to instances of that data type. We change this to a 1. What's it going to print now?
I period.
Huh?
I period.
I period, yeah. There we go, I period. All right. Oh, that's a string data type. How to change the state of a variable using the assignment operator. So here we have, we create a variable named I that represents or labels an integer data. We can't do something like this, by the way. So I is a primitive data type. So the size function like this won't work. This does not compile. It's not a complex data type with the size function defined. But there is something that's equivalent, and it's the size of function, the size of operator. I think that's it. Let me just test that. Don't write that down yet. It works. See the 4? So the size of operator gives the size in bytes of some primitive data type. Also, I believe that we can do it like this as well. It's considered an operator. So that's an equivalent sort of syntax. Now let's take a look at this. So let's create a long called J. Oops. The size of I followed by the size of J. What's that going to print? not hearing. Anyone? What's that? Anyone know what that's going to print?
3.
Huh?
3.
3?
4.
4, and then it'll print 4 for this one. And then what will it print for this one?
Should print 8.
Huh?
Should print 8.
8. Good. Thank you. That's good. Well, I hope it prints 8. Yeah, I shouldn't be so confident. There it is, 4. So it's bytes. See, this I, an int, is 4 bytes, and j is a long int, which is 8 bytes. It's double the size. So you can play with these and see the length in terms of bytes of the different primitive data types. Now, so here's I, and we use what's called the assignment operator to assign a value to a variable. So we start I equaling 3, and then we reassign 33 to I, and then when we print I again, it should print 33. So that's called assignment. So this isn't, that symbol is an equal sign, okay? And that's all. It's just the name of the symbol, equals. What it means in programming, it means assignment. It's an operator. It's an instruction to the computer to take a value on the right-hand side and copy it into the storage that's represented by the label on the left-hand side. That's what it means in this language. In other languages, you might explain that a little differently. I need to compile that. 333. So that's called assignment. Let me show you another form of assignment. It's another assignment operator. The plus equals. This is another way to write this is like this. I equals I plus 4. This is that operator here. So this should print, well, let's go back to here. This prints 3, this prints 33, this will print 37. That's another type of assignment operator. It's the same expression. It does the same thing as this other expression, this other statement. So when I use the word statement and expression, actually this whole thing here is a statement. It ends with a semicolon. And there is a, I'm just going to highlight this. This is an expression within the statement right there. So there's lots of sort of sub-expressions that comprise a statement. You could even think of I by itself as a sub-expression. And that would be an expression inside this larger expression, I plus 4. And this whole thing can be considered an expression, but it also happens to be a statement. It's a complete sort of unit of work, and delimited, terminated by the semicolon. Let's check that we get the same result, 37 there. So we can do this. We can do minus equals. That means take 4 away from I. So this should be 29. And then we have we can do it like this. divided by 7. No, I'm not going to divide by 7. Divide by 2. So take I and divide it by 2. So this is a little tricky. What happens when you take I divided by 2? I is 29. And we take 29 and divide by 2. What do we get? Well, I'll take 28 divided by 2. That's 14. 14 and a half. But I is an integer variable. So what do we do? What would a human do? Human would round up, right? Make it 15. But a computer doesn't round up. The computer truncates. It just drops the fractional part. So I becomes 14. A human starts counting at 1. Computer starts counting at 0. A human will naturally round up. The computer truncates. It drops the fractional component without rounding up. Two differences. There's the 14. There's multiplication as well. That should be 28. It's 28. There's modulo, the modulo operator. What is, wait, this is 28, right? Yeah. What is I mod 3? And by the way, that's the same as this. Replace I by I mod 3. But I'm going to do it this way. I think it's a little easier to see right now. This is the modulo operator. What that means is take I divided by 3. Instead of throwing away the remainder, keep the remainder as an integer value. So it's like in math, they have the modulus in math. Okay, that's what this is. Modulus is that. So it's the remainder. So 28 divided by 3. What's 28 divided by 3?
9.
Well, 27 divided by 3 is 9, right? So, and then there's 1 left over. So it should be 1. It's what's left over. After you take out as many integer values as you can, make it as small as you can, and that's what's left over. So I equals 3 times 9 plus 1, well, 28. 28, which I is 28. 28 is 3 times 9 plus 1. And so there are I mod 28 mod 3. So you do, because of this, 28 mod 3 equals 1. Right? Take out as many 3's as you can. Take out 9 3's. Take out 9 3's and you're left with 1. So let's see that. When we print 9, it should print 1 here. There it is. And we'll be using this modulus operator, so we've gotta know that. All right, what about mathematical operations? Let's look at some of those. So I think we looked at this. Didn't we look at this last time? Oh, by the way, my recording of the last lecture failed, so I did not post that. Right. So last time we covered Visual Studio, and we also covered the first problem of Lab 2. And so the first problem of Lab 2 kind of covers this business here, mathematical operations. Does anybody want me to review that? That probably, yeah, one here, okay. So we were supposed to read 3 values, x, y, and z, from the user. So we want the user to give us values for x, y, and z. So we'll prompt the user like this. We want to tell the compiler that we need storage for an x, y, and z. We need variables x, y, and z. So we just declare those up here. And then we prompt the user for x, and then we read it in. We do the same thing for y and z. Oops. Then we can do things like these mathematical expressions. X plus y times z. And then a new line there to keep things clean. So x plus y times z. So let's develop some test data here. So if we enter in for x, if we enter in 1, and we'll enter in for y 2, and for z we'll enter in 3, then it should print. Let's see, 2 times 3. We did do this first, right? Because multiplication has high precedence. So you do that immediately before the addition. Multiplication has higher precedence, so we do that first. So 2 times 3 is 6. And then this expression becomes 6. And that becomes the right-hand side of this addition operation. So it's 1 plus 6 is 7, so it should print 7. Let's try that. But we need to enter in 1, 2, 3 for data. One, 2, 3, 7. We got it. But to change the order of operations, it's just like in human math. We do this. Now it doesn't print 7. Now it adds 1 plus 2 together. You get 3. And then multiply by 3, and we get 9. One, 2, 3 gives us 9. So we can use parentheses to control the order of execution if we want it to be different than the assumed order of execution. And there, in the assignment, then we ask for things like sign, right? Like sign of x. That's one of them. We went over this last time. This won't compile. Use of undeclared identifier sign. What's the problem?
You didn't include.
Exactly. We need to use the include for that. And it's called CMath. So sign is defined in that header file, CMath. 1, 2, and 3. The sign of 1 is 0.84, like that. And sign works on radians. Learn how to name values using the keyword const. So let's suppose that we had an expression like we want x to be in degrees, not radians. So I want to convert to x to radians. So we want the user to enter in degrees. We want the user to enter in degrees, and we want to take the sign of that. So we need to convert from degrees to radians. How do we do that? I think we multiply by 180 divided by pi. Look at the way I put pi as a constant. So.
You want it the other way.
What's that?
You don't want it pi.
Oh, yeah, it's got to be the other way. Okay. Pi divided by 180. Thank you. But the way I wrote pi here, I put it in uppercase because I wanted to. That's a way to suggest that the value of the variable is a constant. So we can declare that as const pi equals 3.14159. That's all I remember. Let's see if that works. Oops. You see that? Well, let me see what's wrong with that. C++ requires a type specifier for all declarations. It doesn't know that, it knows, we told it constant, so we know we don't want to change pi. But we don't know whether it's a float or a double or whatever it should be. So we have to tell it, we have to give the data type. And use double. So sine of 90 is, what's sine of 90? Is that 1?
Yes.
Yeah. So it's usually close to 1 because our pi is approximate. Turns out to be 1 exactly. Look at that. What happens if we lopped off that 9 there? Still comes out 1? What's going on?
Go down as far as 0.14. It's still 1.
Still going to come out 1? Am I missing something? Change that to 5. Getting desperate. Oh, got something different. Thank God. Is that going to give me 1? No. Oh, it's pretty close to 1, isn't it? Look at that. 999. Anyway. So this pi is a constant. That means if we try to assign it something else, and we say, well, you know, let's try a different value for pi. Let's see if 3.14 is good enough, right? Like this, the same experiment we're doing. The compiler is going to say, hey, you declared pi as constant, and now you're telling me to assign a value to it? I can't do that. Let's see what it does. Error, read-only variable is not assignable. pi is read-only, constant. It's not assignable. We cannot assign. See, it's the assignment operator. They use the word assignment. You got to start using that word assignment. Don't use the word equals in your head. You got to use the word assignment. That's to get the feeling for it. You can read the code more clearly and understand it better if you use the concept of assignment, not equality, assignment. There is equality, by the way. And we use a double equal sign for that. Let's see, I think that's on the list here. Let's wait, we'll get to that later. How to use the complex data type string, we looked at that already. Learn how to invoke functions, we looked at that, or the sign function, the size function for strings, we looked at that. The Boolean data type. Let's do that. So a data type called bool, let's initialize it to true. If B, I'll do it like this. Let me wait a minute. Let me do, let me start with a different example. Integer I, let's have the user input an I. And then if I is greater than 10, then we're going to print too big. Else, we're going to print okay. It's okay. This is conditional. So we declare an integer I, prompt the user to enter in a value for I. We read it in here. This is a blocking call. The program pauses here until the user hits the enter key. And then we do this test. We compare I to 10. We want to know if I is bigger than 10. So if I is bigger than 10, then we do this. If I is not bigger than 10, then we're going to do this. All right? I is 2. It's okay. I is 20. It's too big. 10. What's it going to print? What's it going to print for 10? I is 10. What's it going to print?
It's okay.
Huh?
It's okay.
It's okay. Because 10 is not greater than 10, right? We'd have to be this to get good for that. So we're going to say it's okay. So 10 is okay. So be careful when you start looking at those things. So if I did this, greater than or equal to, that's not, I is no longer okay. I mean, 10 is no longer okay. Now it's too big. Right? That's equal to 10. Greater than or equal to. Now, this is going to be a little redundant here. Oh, let's do it like this. Let's enter in two numbers, I and j. And if I is greater than 10, we'll say if I is greater than 10, or j is greater than 10, then we'll say bad input. So we want both of them to be less than or equal to 10. So if either one is greater than 10, then we're going to say bad input. This operator here, this is called a Boolean operator. The left-hand side is a Boolean value. That means true or false. Boolean is a data type, which is either true or false. Values of the Boolean data type are either true or false. So we have, if the left-hand side is true or the right-hand side is true, then we're going to print bad input. So this is an OR operation, OR. So I'll just do a little truth table here. You know, true or true is true. True or false is true. False or true is true. False or false is false. So we only get false when both the left-hand side and the right-hand side are false. So this is the only case right here this is the special case right here. That's the only time I get false. If it's raining outside or it's snowing outside, then bring an umbrella. If either one are true, we're going to bring an umbrella. They have to both be false. It's neither raining nor is it snowing. Then we won't bring out the umbrella. All right, let's try some numbers then. So if I is 1 and j is 2, what do we got? I is 1 and j is 2. What do we got?
It's okay.
Huh?
It's okay.
Yeah. It's like I is 1. All right, so 1 is bigger than 10. That's false. And j is 2. J bigger than 10. That's false. So we have the case here, false or false. Neither I is bigger than 10, nor is j bigger than 10. So it's false. So we do not do this. This is the true case. This is the false case. So else. Else is what we do if it's false. If the expression, and when I say the expression, I'm talking about this expression. This is the expression. The conditional, the if statement. It's called an if statement. It's also referred to as a conditional statement. That expression there evaluates to true or false. If this evaluates to true, then we do this block of code. If this expression evaluates to false, then we do this other block of code. And by the way, these can be, you know, multiple lines, so we don't have to do it like this. We can have a block of code in there, so we can have multiple lines. So it should say it's okay, and it does. All right. What about, let me build this again. What about 5 and 15?
It's okay.
Huh?
Should be okay.
Should be okay. So 5 is bigger than 10. That's false. Well, 15 is bigger than 10. That's true. So it's false or true.
True.
So true. So we print bad input.
Yeah.
All right. Well, we already saved that. Bad input. We got it. So if one of them is true, then the whole thing is true. It's either raining outside or it's snowing outside. That's a statement. I made that statement. If it's really raining outside, I made a true statement. If it's snowing outside, I still made a true statement. If one of them is true, the whole statement is true. But if neither are true, the whole statement is false. It's neither raining nor is it snowing. So it's actually false. They're both substatements are false. The only way to get this to be false is if both things are false. Of course, if both things are true, it's also true. But let's wait a minute here. Let's try something else. Maybe we want this. Maybe we want I to be bigger than 10 and J to be bigger than 10. If they're both bigger than 10, we'll say bad input. So what is going on with this and? And this is no longer the case here. This is the truth table now. And a special case is when they're both true. They have to both be true for the whole statement to be true, the compound statement, or the compound expression. This is a sub-expression. This is the compound expression here. So for the left-hand side needs to be true, the right-hand side needs to be true for the whole thing to be true. They both have to be bigger than 10 to be bad output. That's a little confusing, bad output. Let me use good input. I think it's easier example. You need them both to be bigger than 10. And here, if one of them is less than 10, then we'll call it bad output. Oh, bad input, sorry. So double ampersand. This is logical and. The two vertical bars, that's logical or. Logical and. The left-hand side and the right-hand side, they both have to be true. If either one is false or both are false, the whole thing is false. You know, like. All right. $23 and 66. What do we got? 23 and 66.
Good input.
Good input. They're both bigger than 10. Both bigger than 10. 23 is bigger than 10. 66 is bigger than 10. We're going to print good input. What about 4 and 44? Yeah.
So it'll be bad.
Bad input because it computes the fall, exactly. The first one is false. And the second one is true, but the second one doesn't matter. First one's false. We're going to print bad input. There it is. Of course, if they're both bad, bad input. And yeah, we're comparing now. Well, there's a lot to do here in this list. So now what about, let's do something else here. I want to show the Boolean variable. Well, we're not gonna, we'll eventually use this. B, I'll say, we'll say good, I'll say good input is true. And now, if I, so we're going to assume that it's if it's good input. So if I is less than 10, then good input is set to false. If j is less than 10, good input is set to false. Now we can use good input. I don't need that. See, that's code duplication. I'm just going to put that out there. I don't like that code duplication. I have the same statement twice there. Just put it on the outside. It's the same thing. That's a simplification. It's good to avoid code duplication. So anyway, now the argument here to this if statement is a Boolean variable. See, we declared it bool here. Good input is bool. But we can use that in these if statements, just like that. So we're going to start by setting good input to true. We're saying we're going to assume, oh, the user entered in two values that are bigger than 10 or equal to 10. But, so we're going to assume that it's true. Assume that the user input is true. But now let's check, well, if the I turns out to be less than 10, well, let's change, good input is false. Or if j is less than 10, then good input is set to false as well. So we could do it like this. So there's so many ways of doing this. I think we had bigger than 10, right? That's how we did it. Let me change it to that. If j is larger than 10, oh, no. This would be equivalent to what we have. All right, 22 and 4. What does it print? I is 22 and j is 4. I is 22. Huh? It's going to print bad input. Let's see. If I is 22, then this thing is false, right? Let me go back to here. Let's think this out carefully. I is 22. And j is 4. Did I get that right? I is 22 and j is 4. Good input is set to true. If I is less than 10, well, this is false here. So we do not do this. And notice there's no else. I could have put an else here. But I didn't. We're dropping, so else is optional. So these if statements they don't need an else clause. So I is less than 10, well 22 is not less than 10, so this is false. This is false expression, so we do not do this. Then we come down here, j less than 10, well j is 4, 4 is less than 10, that means this expression is true. If that expression is true, then we're going to do the statements that are substatements within the if statement. This is a substatement within the if statement that I have highlighted here. we're going to change our minds about the good input. It's currently set to true, but now we're going to set it to false. We're going to change its value to false. And then when we get down to here, get input is now false. So we do not do the true part of this statement. We do the false part, which is here. So we're going to print bad input. Let's see. Let's make it. Let's figure out how we're going to make it print good input. Well, this thing has to be true, right? But we initialize it to true here. That means we need both of these to be false. So we need I and j to be less than 10. I'm sorry, we need both of these to be false. So I and j have to be greater than 10. So we need both I and j greater than 10 so that we do not set good input to false. Now let's try that. Good input. So they're both bigger than 10. We figured that out. So these are logical expressions. This is how you express things, logically in computer languages. This is C++, but it's the same. This could be probably any language, really. They all look like this, almost all of them. I'm going to talk a little bit about this. This right here, see this? I've highlighted. That is one statement. It's one statement. That's a statement inside main. Here, look, I'm going to show you this. This is the first statement inside main. This is statement 1, statement 2, statement 3. Blank line is not a statement. Statement 4, statement 5, statement 6. These are not statements, they're comments. This is statement 7. This is statement 8. Look, so far all these statements end with semicolon. You see that? It's a statement delimiter. But this whole thing right here, all the way down to the bottom, this is statement 10. This is a compound statement. It's a statement that has substatements. This statement 10, maybe I'll put the 10 up here. This statement 10 has two substatements. This is one substatement, and here's another substatement. So these are considered substatements. This here I've highlighted, that's a single statement. Notice we don't end with a semicolon. We could put a semicolon here, but we don't have to, because when you end with a closing brace, you don't need a semicolon. And then this statement here, this is the 11th statement in the main function. Main has 11 statements. One of the statements, statement 10, is complicated. It's complex. It has substatements in it. But we can sort of think of that as hidden from main. Main just sees itself as, I've got 11 statements. I'm going to execute one after another. And then I'm done. So main says I got 11 things to do. When it gets down to statement 10, well, you can think of it, this statement as saying, well, I've got a lot of other things. I'm complicated. I have substatements. I have one of two statements that need to run, depending on what good input is equal to. Now that's how you look at that. Now, this substatement here, you see how I have it indented? That's to show visually that's a substatement. The compiler doesn't require that. We could put it out like this. Oops, not like that. That won't work. We could do it like that, but it's hard to understand. It's hard to see the logic. We want to show that these are substatements of the if statement. So we indent them relative to that if statement, the beginning of the if statement. This is very important. And when you submit assignments, you'll have points taken off if you don't properly indent your code. It's extremely important because it's not readable by humans. It has to be readable by humans. And notice the if statement, statement 10, is also indented relative to main. Because this if statement here and all the other statements, the 11 statements inside main, they're all inside main. They're all sub-statements of main. And you could think of this, in a sense, as a statement. It's a function definition. You can think of that as a unit, main. Compiler says main, I've got a function main. That's one thing. And it's comprised of these subparts, these substatements. There's 11. And see, they all have the same indentation. And inside here, we have a compound statement, this if statement, and it has substatements. So we indent another level. So these are 2 levels of indent. So this is very important. You want to follow this indenting pattern when you write code. Just a little bit more about this. There's different styles. This is the most common style that I'm showing right here. Another style would look like this, that the opening brace is down one line. So there's a style right there. This is not as common as the one I just showed you, but this is also, it's valid. This is a valid style. People can read this. Another possibility is just to keep the else in one line like that. That's another sort of version of this, you see. Whatever you do should be consistent. Don't mix styles in your code. Be consistent. That's another requirement of the course, by the way. And I'll show you this. In the syllabus, there is a list of readability criteria, and you need to adhere to these criteria when you write and submit code. Logical indentation, that's what we've been talking about. Consistent means whatever style you need to stick to a particular style. Like this is okay, but this would be okay. Well, it's not a mix, but if I did something like this, this is inconsistent indentation. This brace, this opening brace is on the same line as if. Here we have the opening brace on the next line, so that would be inconsistent.
Would it be considered inconsistent as well because of the brace on the in main line?
Well, not exactly, because this is a brace for a function definition, and this is a brace for an if statement. So you could argue that they're 2 different kinds of statements. So that my style is to indent differently for those 2 different kinds. So I didn't use that as an example, but I do believe that there is an element of inconsistency there as well. Yes, you're right. Although you do see this sometimes, that functions are given more space. And you might see that like this. But I just play it safe. And by the way, my style changes over the years, and it's kind of arbitrary. Right now, I'm not an individual anymore. I'm just going to do whatever is the most popular in a given language I'm working in. I'm going to follow that style. So if we're working JavaScript, I use a different style. I work in C#, I'm using a different style, different naming conventions. That's just what I'm doing now. I use whatever the most common as an instructor. But if you're at work and you're in a team and you've got a code base you're working on, pretty much you're going to want to stick to what's in that code base. If it's really sloppy and messy, then that's okay for you because it means you got a job, right? If everything was clean and easy to debug, you might not find work. That's the sarcastic point of view there. All right. Let's see what else we're going to do there. We have another 5 minutes.
So if our style changes from like one lab to another, we aren't going to be judged on
You can change
just within one lab.
within one
File.
exercise.
Okay.
Yeah. You can have exercise 1 could follow this style, and exercise 2 could follow a different style. That's okay. All right. What about now? There's loops. We don't have time to do that today. And the difference between floating point and integer division is very important. How to do rounding. If you look here on exercise 4, this actually is a very hard problem, so don't stress over this problem. I will show you how to do this problem. You should try it. But it's the purpose of this problem is to make you aware of integer division, round off errors, and the difference between how a computer represents a number and how numbers, say, exist in a theoretical perfect sense in mathematics. So, like if you have the value 1/3, 1/3 is a definite number. It's well defined. But in the computer, if you store 1/3 as a single floating point value, you can only represent it as an approximation. So to store 1/3 in the computer, you'd actually need to represent it as two things, a numerator and a denominator, because you can't represent it as a single floating point value precisely. But that's what we do generally, and so there's some error gets introduced into your calculations, and if you loop on that and use the value over and over again and keep modifying it, then you get that little error starts to propagate and get larger. Although this doesn't cover that issue, but it does cover the issue of integer division versus floating point division. So we'll talk about that next time, and we'll also start talking about loops. One last thing, exercise 2. Exercise 2 here is an exam that I gave some time ago, and this will resemble what your first exam looks like. So I want you to start practicing solving these exam problems. And the way you submit this is you don't need to code this on the computer. You just think it out. You read the program, figure out what it prints, what it computes, or answer the question, whatever it asks, as if you're in an exam setting. You don't have a computer or a calculator with you. There's no calculator in the exams. You don't need it. And come up with these answers on your own. And then put your answers in a single file and submit those as if like you were submitting a program. And send those to Jaron, CC me. If you want to go a step farther, practice like you're taking an exam, work these out in your head. And then when you're done and you wrote down your answers and you're confident about them, then try to code these up and run them, in the computer to see if you get the right answer. And it's not always possible to do that. Like for instance, here, this one here. How many times does the body of the for loop run in the code? So you wouldn't know that by coding this up and running that program. Although you could put a counter in there and figure it out. So this one you can't really verify by coding. You can, but you'd have to add some code to this. Does everybody understand that? This exercise 2? And the upcoming exam? I want you to be ready for this exam, okay? So I'm preparing you for the exams in many cases.